Welcome to Trane Engineers Newsletter Live. I'm Jeanne Harshaw, and in today's program we'll be addressing various myths, claims, and misunderstandings in the HVAC R marketplace. The broad range of topics we've included in today's program are based on conversations and feedback our application engineers have with our customers. And to cover them today, we have applications and systems engineers Dustin Meredith, Lee Cline, and Mick Schwedler. We have an information-packed program today, so let's get started with the first myth. Lee, low delta T is unavoidable in large chilled water systems, isn't it?
Jeanne, this is an undeniable fact. Few would deny that low delta T is a rampant problem in chilled water systems. But is it inevitable? And should we care? First, let's talk about why we should care. The answer is energy, and it can be a lot of energy. We should all know the formula for tons by now. If we arrange and solve for GPM, we see that because the delta T is in the denominator, if the delta T goes down, the GPM must go up to provide the same tons to the system. Said another way, at a given tonnage, the system GPM is inversely proportional to the delta T. We know from system effects analysis that the frictional component of the piping pressure drop, or head, varies by approximately the square of the flow. Examining the water flow work equation, if the GPM goes up proportional to flow and the system head goes up by the square of the flow, the required water horsepower goes up by approximately the cube of the flow, or the cube of the delta T drop. So a decreased delta T first and foremost results in a dramatic increase in pump work and power. Don't confuse these system effects with the pump and fan affinity laws. This is the description of the required system pump work. It's the same no matter what type of pump modulation is employed. Of course, there can be secondary impacts to low delta T. In systems with constant flow chiller pumping, low delta T can require additional chillers to be brought on earlier than what is optimal to meet the increased system flow requirement. This may result in less efficient chiller plant operation. So severe low delta T is clearly bad, but is it inevitable? We would say no. Let's see why. Here we see a chart of the unloading performance of an ASHRAE certified coil in a VAV system. The coil was selected with a 16-degree delta T. This aligns with the ASHRAE 90.1 2016 chilled water coil delta T requirement of 15 degrees or greater. This chart represents typical coil performance. Notice that as the load decreases from its 100% selection point, its chilled water delta T initially rises. Then it drops slightly through the transitional flow region and then rises dramatically at low loads because of the water retention time in the coil. This is not a special coil. This is the performance predicted by every heat transfer method calculation. You're probably thinking, yeah, but what about laminar flow heat transfer? Laminar flow has a lot less impact on variable flow cooling and heating coil delta T than you think. I don't have time to discuss that here, but I'd refer you back to the spring 2015 E&L on coil selection and optimization for a discussion of that. As an aside, what would be the variable flow coil delta T performance if the coil had internal heat transfer enhancements, or what is sometimes called turbulation? The delta T actually rises dramatically and the flow drops proportionally throughout the load range. This technology is often rejected because of its higher full load waterside pressure drop. But with this type of heat transfer performance, the pump energy penalty quickly goes away at part load. This can provide more efficient annualized operation. Let's set this aside for now, but we highly recommend the consideration of internally enhanced tubes in variable flow chilled water systems. If this is how coil heat transfer works, Then why is their system low delta T? There are a number of things that can impact coil and system delta T performance. I'm going to give you what I believe are the top 5 reasons for system low delta T. One common cause of low delta T is 3-way valves. Let's see how a 3-way valve destroys system delta T. For this example, we'll take a simplified look at a coil with 50% airside loading. With nice cold 42-degree chilled water, the coil returns 59-degree leaving water for a 17-degree coil delta T. But 50% of the 42-degree supply water is bypassed around the coil by the 3-way valve and mixes with the coil leaving water temperature. This results in a wastefully cool 50.5-degree system return water temperature at an 8.5-degree system delta T, exactly half of what the coil is producing. It doesn't matter if the flow goes through the coil or around. The pump still has to do the work to get the water through the system. Bottom line here, eliminate all or as many as possible 3-way valves in variable flow systems. Next up, supply air set point depression. This applies to coils with either leaving air temperature control or direct space temperature control. For this example, we'll look at VAV leaving air temperature control. Here's a chart that shows a coil selected for a 55-degree supply temperature. It returns a little over 16 degrees of delta T at its design conditions. But what happens if the operator turns the set point down to 52 degrees in response to an occupant complaint? It requires much more flow for the coil to make that condition, and the delta T drops to just over 11 degrees. Heck, it's going to be hot tomorrow, so I think I'll turn the supply air set point down to 50 degrees to make sure I don't have any complaints then. Tomorrow's result? A full load delta T of 8.5 degrees, requiring almost double the design flow, if the pumps can produce it, and close to 8 times the system pumping energy. Based on my experience and case studies I've read, this is the #1 ongoing cause of excessive low delta T. Coil control set point discipline is critical in the maintenance of system delta T. Many systems are adding features that limit the ability of occupants and operators to override set points, or notify operators of depressed set points, and in some cases, scan the set points periodically and return them to their intended values. Another thing that causes a coil to produce troublesome low delta T is higher than design supply water temperature. We see that a rise of 5 degrees in the supply chilled water temperature to the coil from 42 degrees to 47 degrees causes the coil's delta T to fall from 16 to about 7.5 degrees. An increase to the supply water temperature of 50 degrees drops the delta T to almost 5 degrees. The cause for the reduced low delta T is the reduction of the heat exchanger LMTD. I think of LMTD as the driving force for heat transfer. This does not mean that chilled water reset should never be used in variable flow chilled water systems. When a system is operating at low pump energy, employing some chilled water reset to save chiller energy at the cost of a bit of additional pump energy may be the correct energy move. As in all optimization, it's a balance. But clearly, aggressive chilled water reset at higher loads can definitely result in undesirable low delta T. Chill water reset should only be used at part load after pumping power has already been reduced. 3 down, 2 to go. Improper control valves is a big category. There are many things that can result in problematic control valves. Here are several control valve related deficiencies. The bottom line here is that anything that causes a valve to lose accurate and stable flow control under any operating condition will result in lower than desired waterside delta T. To avoid valve-generated problems, it's imperative for the engineer to specify high-quality valves selected for the operating conditions of each specific air handler. This was driven home to me recently during work at a high-rise building in Atlanta. Each floor had identical air handlers and chilled water control valves. The chiller plant and system pumps were in the basement. Since the air handlers on the lower floors were closer to the central plant, they are subject to a much higher system pumping pressure than the higher floors. In fact, when I arrived, the control valve on the second floor air handler was 100% open because the supply air set point had been set extremely low. In checking, we found out that it was flowing just a little over 3 times the coil design flow at a part load condition. Now, the valves were likely oversized even for the top floor air handler, but they were definitely too large for locations in the system closer to the pumps. Properly selecting control valves for their design flow and their location in the system is important for good control and delta T. Which brings us to the question of pressure-independent control valves. There are 2 technologies of PI valves, mechanical and electronic. Both can work equally well, and each has its own set of advantages. The question is, are pressure-independent control valves needed to assure good system delta T? This is a question of much debate among engineers. My answer, no, they are not required to get good control, but they sure do make it a lot easier and sustainable. If you're not sure you can get high quality, properly selected, location-specific valves installed on a job, then by all means, specify quality PI valves. It will be well worth the customer's investment. Finally, tertiary pumping, also known as bridge tender or simply bridge pumping circuits. These circuits are applied out of the age-old engineering principle, if you're not sure it will work, add more pumps and valves. Bridge tender circuits are a throwback to the days of constant flow, 3-way valve air handlers, and constant speed pumps. They are installed with the stated mission of providing additional pumping pressure to buildings or coils that may be underserved by the central plants. Sometimes they are installed under the guise of increasing system delta T. Unfortunately, they often result in exactly the opposite and dramatically decrease system delta T. The problem lies in the presence of the bypass valve in the circuit. This diagram shows just one configuration of a bridge tender circuit. Depending on the designer, the bypass control valve may be configured several different ways. The problem is that no matter how it's configured, if its control goes wrong, it will allow unused chilled water to bypass directly into the system return water. System delta T drops, system flow increases, and pumping power increases. If you have a system that may need additional pumping pressure, rather than a bridge circuit, we would suggest application of a straightforward pressure boosting pump configuration with VFDs for speed and pressure control. Then, to protect against low delta T, consider applying pressure-independent control valves downstream of the booster pumps. That is for the time in the life of the building when the operator decides they need more booster system pressure, which can destroy the control capabilities of standard valves. We would suggest that maintaining system delta T at or above the selected value should be relatively easy if the system includes properly selected and sized AHRI certified coils, set point limits, high quality control valve selections, and proper controls commissioning. Low delta T unavoidable? We don't think so. Jeannie, this myth is busted.
Nice job, Lee. Next up, arbitrarily designing for a set 55-degree supply air temperature is a common design practice. Is this practice still valid for today's changing loads? Are there alternate ways to handle the needs of today's buildings? Dustin?
The continuing emphasis on the overall energy use of a building has resulted in substantial leaps forward in building load reduction. LED lighting, more efficient computers, better fenestration design and shading, etc., all have served to reduce the sensible cooling loads in a space. The impact of this reduction must be understood, and it may require a change to traditional design practices, discharge air conditions in particular. Let's use a psychrometric chart to illustrate the effect these changes have on a basic system. At full load, outdoor air is mixed with return air, and this mixture passes through the coil to be cooled and dehumidified. Then, this cold, dry air is delivered to the space where it absorbs sensible heat and moisture. In this more traditional example, the space temperature is controlled to a set point, and the resulting relative humidity in the space is 52%. Now assume that the building design changes to use a much higher quality glass, along with more efficient lighting and office equipment. This change will serve to reduce the sensible portion of the design load, a 47% reduction in this example. When the sensible heat load is reduced, our sensible heat ratio, or SHR, also reduces, resulting in a steeper SHR line on the psychrometric chart. If the system were to be arbitrarily designed with a 55-degree supply air temperature, the resulting room conditions will fall on this steeper SHR line. This results in a higher room relative humidity than desired, an increase of 5% in the example shown. So to maintain the same humidity condition in the space, we need a lower dew point leaving the air handler. Simply lowering the supply air temperature might be the first thought that comes to mind. Combined with the steeper SHR line, we would then be able to meet the original humidity goals. But now we are dealing with a supply air temperature that may require reheat at non-design conditions. So to get a lower dew point without lowering the supply air temperature, there are a number of dehumidification approaches that could be used. Let's focus on two of them, cool reheat and type 3 desiccants. First, the common cool reheat approach. With this type of system, the mixed air is overcooled to remove the moisture from the air. The air is then reheated to catch the SHR line back to the desired room air condition. A cool reheat system uses energy. It requires more cooling energy to cool the air, and it requires reheat energy, recovered or generated, to heat it back up. Alternatively, there is a desiccant option that can reduce the air handler dew point while reducing energy significantly, a type 3 desiccant. CDQ, the name we use for our type 3 desiccant solution, requires a little more explanation. The most basic CDQ configuration places the wheel in series with a cooling coil. The upstream half of the wheel desorbs moisture to the mixed air stream, while the downstream half adsorbs moisture from the supply air stream. This series approach puts all of the dehumidification work on the cooling coil. The cooling coil now becomes a better and more efficient dehumidifier. Let's step through the process with an example. First, let's look at the air leaving the cooling coil. In the example shown, air leaves the coil at 50 degrees and 97% RH, a condition where the desiccant has a high affinity for water vapor. As the air passes through the wheel, the desiccant adsorbs some of the water vapor. The final supply air contains less water vapor than the coil leaving air, 10 grains less in this example. With this removal of water vapor, some heat will be gained from the adsorption process. In this case, a resulting supply air dry bulb temperature of 55 degrees and a dew point temperature of 43 degrees. Let's make sure this part is clear. We were able to get a 43-degree dew point even though the coil leaving air temperature is at 50 degrees. Where does this adsorbed water vapor go? The answer is that the wheel slowly rotates and this water vapor is released upstream of the coil. Mixed air enters the wheel at 80 degrees and 50% RH. At this relative humidity, the wheel desorbs water vapor into the mixed airstream without the need to add heat to the airstream. In fact, desorption actually cools the air. The water vapor that was adsorbed after the cooling coil re-enters the airstream before the coil. This raises the dew point of the air entering the coil from 60 to 64. It also pre-cools the air from 80 to 75 degrees. The transferred water vapor then condenses on the cooling coil and the process starts again. The end result is that the coil does more latent work and breaks the dew point barrier. That is, the dew point of the supply air is lower than the dry bulb temperature of the air leaving the chilled water coil, yet all the dehumidification work is still done by the coil. Let's see how a CDQ system would help the example we used earlier. The mixed air enters the wheel and regenerates the desiccant, removing the water vapor that was adsorbed downstream of the cooling coil. The air leaving the wheel is then cooled and dehumidified by the cooling coil. The air leaving the coil then passes through the wheel again, where water vapor is adsorbed by the desiccant and the supply air leaves at a lower dew point. Again, the supply air dew point temperature is lower than the temperature leaving the coil. The supply air then catches the SHR line back to the desired room condition. Applying CDQ to our example, we can see that a CDQ system can get us back to the desired RH without the need for a cooler supply air temperature. In fact, our supply air temperature is now much higher, 63 versus 55 degrees before. For more information on CDQ and dehumidification systems in general, see the Improving Dehumidification in HVAC Systems Engineers Newsletter Live materials. So is it true that a 55-degree supply air temperature is adequate for today's loads? No, this myth has been busted. To maintain comfortable humidity levels, we need to consider the discharge air condition and its impact on the space, and not just the discharge air temperature.
Nice job, Dustin. There's a fair amount of confusion when it comes to refrigerants in this industry. The next myth is one we hear often enough to include in this program, which is ASHRAE Standard 15 has to be updated before new refrigerants can be used. Mick, can you break this one down for us?
Let's start with a little background. There are two ASHRAE standards that address refrigerants, and they work together. Standard 34 establishes a simple means of referring to common refrigerants and a uniform system for assigning reference numbers, safety classifications, and refrigerant concentration limits to refrigerants. Standard 15 is a safety standard to specify safe design, construction, installation, and operation of refrigeration systems. Now, Standard 15 doesn't have information for refrigerants within it. Instead, Standard 15 uses the Standard 34 safety classification and refrigerant concentration limit, or RCL, for a specific refrigerant, and defines the requirements for the refrigerant's safe use based on that classification and RCL. So why might people think they can't use refrigerants that are newly classified by Standard 34? The confusion likely comes from the creation of a new safety class by the ASHRAE Standard 34 Committee. The optional 2L flammability class falls between the no flame propagation Class 1 and the lower flammability Class 2. 2L indicates that although the refrigerant will propagate a flame, it burns slowly. But today, ASHRAE Standard 15 does not set specific requirements for 2L refrigerants. So some think they can't be used. That's incorrect. Since classification 2L is a subset of Class 2, from a Standard 15 perspective, Class 2L refrigerants are presently treated the same way as Class 2 refrigerants. There may be changes to Standard 15 in the future to create different requirements for 2L refrigerants. ASHRAE, along with the U.S. Department of Energy and AHRI, are sponsoring $5.2 million of research into 2L refrigerants to learn more. Now, to update Standard 34, addenda are prepared by the committee and sent through a public review process to reach consensus. Since the 2013 version, 35 addenda were approved and are now in the 2016 version of Standard 34. 3 new refrigerants and 27 blends have been added and can be used, and some examples are shown on the slide. Most of the new refrigerants do not fall into the 2L category. Standard 15 applies to these as well. The reality is that all refrigerants that have received an RCL and safety classification per Standard 34 can be applied using the requirements of Standard 15. So this myth is busted.
Thanks for the clarification, Mick. Hot gas reheat is often used to improve the part load dehumidification performance of single zone systems with a constant speed fan. But single zone VAV units don't need hot gas reheat, right? Maybe as a precaution for certain applications? Dustin, what do you think?
To help answer these questions, we will consider an example elementary school classroom in Jacksonville, Florida. For this example, the system supplies 1,500 CFM of air at about 55 degrees to offset the space-sensible cooling load and maintain the desired 74-degree dry bulb temperature in the classroom. The ventilation requirement for this classroom is 450 CFM. In the slides that follow, we will start with analyzing a constant volume system and then see how things change with a single zone VAV system. Plotting the system on a psychrometric chart, the resulting relative humidity in the classroom is about 52% at full load design conditions. Now let's look at an example part load condition, like a warm, humid day. When the sensible cooling load in the space decreases, the system with a constant speed fan continues to supply a constant volume of air to the zone, 1,500 CFM in this example. Meanwhile, the compressor cycles on and off, which results in a warmer average temperature delivered to the zone. Although this control action successfully maintains the zone dry bulb temperature at set point, the cycling compressor reduces the amount of moisture removed and zone humidity rises. At this example part load condition, the resulting zone relative humidity rises to 67%. To underscore the severity of this concern, let's introduce another challenging part load condition, a mild rainy day. Because of these moist outside air conditions, the constant volume fan system brings humidity into the space and results in an even higher humidity, 73%. A common way to improve dehumidification performance at part load is by using a cool reheat approach. With package DX equipment in particular, it's fairly simple and cost-effective to recover heat from the refrigeration cycle. The refrigerant vapor leaving the compressor is very hot. In the dehumidification mode, this hot vapor is directed through a reheat coil located downstream of the evaporator coil. This is commonly called hot gas reheat, and it offers a cost-effective approach for site-recovered reheat. In order to limit space humidity to 60%, a constant volume system with hot gas reheat will overcool the air to dehumidify it, and then reheat it to prevent overcooling the zone. This improvement comes at a price as it requires more compressor energy, and because of the reheat coil pressure drop, slightly more fan energy. Of course, the benefit of hot gas reheat is that it can be controlled to maintain a lower humidity level, if desired. But that would result in even more compressor energy use. While the heat used for reheat is recovered energy, it's not free. It comes at the price of increased compressor energy. Bottom line, space humidity can be maintained with a hot gas reheat option. Now let's consider a single zone variable air volume system. Remember that this system operates with a discharge air temperature that is lower than what a constant volume system would supply when operating at part load cooling conditions. The VAV system continues to deliver cool, dry air at part load conditions. This colder, drier discharge temperature has dehumidification benefits at part load. Let's plot a variable speed fan operating at the peak dew point condition. When the sensible cooling load in the space decreases, the system responds by reducing fan speed, which reduces airflow. At this example condition, supply airflow is reduced from 1,500 to 900 CFM. Reducing the airflow allows the coil to remove more moisture and lengthens the compressor runtime, both of which improve dehumidification performance. At this same example part load condition, the relative humidity in the zone improves from 67% with a constant speed fan to 57% with the variable speed fan. For the variable speed fan system, the load on the cooling coil is 4 tons, and the fan moves 900 CFM, compared to 1500 CFM and 3.7 tons with a constant speed fan. We may now be using more compressor energy, but we have vastly improved space humidity, all while benefiting from much lower fan energy. Similar results for the challenging mild rainy day condition. For this example classroom, the variable speed fan results in much better dehumidification, 60% RH compared to 73 with a constant speed fan. So a variable speed fan doesn't require hot gas reheat, correct? For many applications, the variable speed fan might do a good enough job of limiting indoor humidity levels. So you may not need to equip the system with any other dehumidification enhancements. But there are other applications where enhancement like hot gas reheat could be useful. Consider hot gas reheat if a project requires lower space humidity levels than a single zone VAV system can achieve. The variable speed fan will limit indoor humidity levels most of the time, but the reheat can kick in if it's ever needed. For spaces with wildly varying loads, or for jobs with oversized units, hot gas reheat is especially valuable. Let's look at an example. Suppose the preceding examples assumed a chilled water air handling system where we were able to select equipment for specific airflow rate. But if our school instead used packaged DX equipment, we could be limited on airflow flexibility. To ensure adequate cooling capacity at full load conditions, suppose we must accept a higher than desired airflow of 1750 CFM. At this higher than desired airflow, the humidity at design increases to 56% RH. At part load, our problem is even worse. Our RH is now at 59%. To get back to the desired space level of 52% RH, a dehumidification enhancement like hot gas reheat is necessary. The reality is that there are many applications where the equipment is way oversized or is sized for a design load that is much higher than the typical operating load. If the unit is significantly oversized, it doesn't take much of a reduction in space load before the fan has reached minimum speed and the supplier temperature set point needs to be reset upwards. So when it comes to humidity, oversizing is bad, even if you have variable speed fan control. You should really consider hot gas reheat for any space where this might occur. As an example might be an auditorium, where the design load is based on a person sitting in every seat. But this space will often be used when there are only a few occupants in the zone. The unit is not technically oversized, considering those few times when full occupancy occurs. However, it performs like it's oversized for the vast majority of operating hours. Gymnasiums and church sanctuaries are other similar examples. Basically, consider hot gas reheat for any space with extreme variable occupancy. Please note that the example presented earlier is for comparison purposes only. The resulting space RH level for any particular application depends on the combination of sensible and latent loads in the space and the concurrent outdoor condition. So let's summarize. Avoid oversizing equipment whenever possible and make sure the equipment is being controlled properly. If additional dehumidification performance is necessary, add hot gas reheat. So is it true that single zone VAV units don't need hot gas reheat? No, this myth has been busted. Hot gas reheat can be used in conjunction with a variable speed fan to improve part load dehumidification performance. It's especially valuable for space with extreme variable occupancy or if the equipment is oversized.
Nicely done, Dustin.
Let's keep moving.
Now, Lee, I know this next myth is one of your pet peeves, so you take it away.
Jeanne, I love to study and understand physical principles, and I hate to see them misapplied. In the HVAC industry, the affinity laws are by far the most misapplied of principles. I have to admit that the myth that you slap a VFD onto anything and you get full advantage of the affinity laws is one of my pet peeves. This myth is most often applied to fans, pumps, and centrifugal compressors, all of which can be classified as dynamic pressure devices. A dynamic pressure or compression device is one that creates pressure by accelerating a medium such as a fluid or gas, and the fluid's velocity is then converted to static pressure based on the principle of conservation of energy. The thing to remember is that these principles are limited to predicting the performance of dynamic compression devices, but they often don't define the system pressure and flow requirements. So let's ignore efficiency changes with flow and speed, and let's look at the affinity laws again, but in a little different order than usually presented. The affinity laws say that the pressure produced is proportional to the square of the speed. If the system allows, the flow produced is proportional to the speed. And finally, when the system characteristics allow both of the above to hold true, then the power required of the device varies with the cube of the speed. I'm a visual learner, so let's look at these principles graphically. So, for a device installed in a system with frictional-only pressure losses, we can see again that as the rotating speed increases or decreases, the pressure produced varies proportionally to the square of the speed. The flow produced varies proportionally to the speed, and everyone's favorite, as the rotating speed increases or decreases, the power required varies proportionally to the cube of the speed. All of these go together. However, the device is at the mercy of the system, and its operation must comply with the system requirements. What if the system does not follow the same pressure and flow relationships as generated by one of these devices? First, let's examine a common example of a system that has the same operating characteristics as of a dynamic compression device, and then one that does not. The two best HVAC-related examples of systems that comply with affinity laws are cooling towers and single-zone VAV systems. They may be the only two that comply well. Let's look at an example to internalize what that means. Here is a cooling tower that, at its design conditions, requires 15 kW of power. This is the 100% flow, 100% pressure, 100% power point of operation. Here is the same cooling tower at 50% load and therefore flow. What is the tower's power requirement here? Because as a system, the tower operating characteristics are the same as, or said another way, comply with the affinity laws. At 50% flow, it requires 25% fan pressure and consumes 12.5% power. Its fan power draw is now only 1.9 kW. To make a point about VFDs on towers, I always tell customers that ASHRAE is wrong in the 90.1 standard to give an exemption to the use of VFDs on any cooling tower fans. Cooling towers are absolutely the best application of variable speed with a great return on investment. If cooling towers are a great example of the affinity laws, what are some examples of systems that are not compliant with those laws? Pretty much any HVAC system or component that isn't one of the other two. Any system that has a control valve, pressure control set point, or fixed static lift, or heat exchanger approach, minimum flow, or refrigeration lift in the system. These don't follow the same flow and pressure principles as the affinity laws assume. When looking at one of these systems, we must remember that the device must operate to meet the worst case system requirement, flow or pressure, so it's important to examine both. Let's look at an example. The pumping power for a single chiller, variable primary flow chilled water system with changing loads. The first question that must be asked is, what might cause a VPF system not to follow the affinity law principles? First on the list is the pump minimum speed limit. Most pump motor combinations have a minimum speed recommended by the manufacturer to ensure motor cooling or pump reliability. Let's say the pump minimum speed requirement is 20 Hertz, or about 33% speed. The pump can never be allowed to operate at less than that speed, no matter what the system load is. We see that below 33% system load, the pump speed cannot go to 0 as the affinity laws would like, but are locked at 33% minimum. Since the pump impeller follows the affinity laws when it's turning at 33% speed, the discharge pressure also remains at about 10% of design rather than decreasing to 0. The impact on pump power is that rather than decreasing to 0, it remains at about 3% of design. In reality, it's actually quite a bit higher because of pump, motor, and drive inefficiencies, but we're ignoring those here. A submittal from a good pump selection program would include them. You might ask, what about system flow? How does the system flow decrease below 33% if the pump speed does not? Won't the system be overcooled? No, it won't. In a variable flow chilled water system, the coil valves control the flow. The pump's job is to produce pressure. So even though the pressure remains a bit elevated, the control valves throttle their individual flows. As system flow drops, even as the pump speed remains elevated. A second factor that will affect the pump's operation is the system differential pressure set point. Let's assume we have a system with a 20-foot differential pressure set point and 80 feet of frictional loss for a total pumping pressure requirement of 100 feet at design load. This warps the system pressure requirement curve upward. Its minimum operating pressure point is now 20% of design. Note how significantly this changes the pump pressure requirement. In order to meet this system pressure requirement, the pump speed control will have to rise as well. In order for the pump impeller to meet the 20% pressure requirement, the speed can never decrease below about 45%. Of course, this affects the pump's power curve also. The pumping power is higher at all loads. It bottoms out at a minimum of about 9% of design at no load. 9% at no load is not huge, but it is much higher than the affinity laws would predict. What is more concerning is that the pump power is higher at all system load points. There are optimizing control methods to reduce this penalty, but that's a discussion for a different day. Finally, what is the impact of the chiller manufacturer's required evaporator minimum flows on the pumping system? For this, we will assume the chiller evaporator has a minimum flow of 50% or a turndown of about 2 to 1. More would be better, but less flow turndown is not unusual. If the minimum flow allowed for the chiller is 50%, the pump speed must be held at a minimum of about 50%. In fact, because of a lower system pressure drop, the speed would likely decrease a little more with load, but not a lot. Because we don't have specific system and pump curves to dissect, we will assume the worst case of 50% speed. At 50% speed, the pump would generate 25% of its design pressure. The control valves would have to throttle against that pressure to control the individual coil flows and capacity. Here we see that the pump power flatlines at about 12.5% of its design value. But remember, we said that the pump must meet the worst case of the system requirements. So let's combine the differing power requirements to see what that looks like. If we overlay the pump power impacts of the 3 non-compliant system characteristics, pump minimum speed, heat exchanger minimum flow, and differential pressure set point, we see that below about 25% load, the chiller's minimum flow requirement, represented by the red line, sets the pump's power use. Above 25%, the system differential pressure set point, represented by the blue line, sets the pump's power requirement. Looking at the graphic, you might think that the overall power increase doesn't look all that great. But below 50% load, the actual power used is 2 to 4 times greater than predicted by the affinity laws. This could easily represent a 50 to 100% increase in the actual annual pump energy use as compared to what the affinity laws would predict. Let's take this one step further. What if the chiller's minimum flow requirement was 70% of the selected value rather than 50? We are seeing a number of chiller submittals in this range of minimum flow. With a 70% minimum chiller flow, the pump speed would bottom out at about 70%. The pump pressure would bottom out at 49%. And the minimum pump power would be about 34% of design. Looking at some part load differences, at 50% load, the predicted power is only 12.5%, but the actual power is 34%. At 25% load, the Affinity laws predict 1.5% power, and in reality, it's 34%. Those are significant energy use differences. This magnitude of difference is not uncommon or extreme in non-compliant systems. So while the Affinity laws do predict the ideal performance of dynamic compression devices in frictional flow loss systems, there are many more HVAC systems that don't comply with these operating principles. A non-compliant system is any one that has a control valve, fixed static lift, a pressure control set point, a required minimum flow, or back pressure in the system. If any of these exist, the system does not follow the same flow, pressure, and energy principles as the Affinity laws assume. This is not to say that applying variable speed technology will not save some energy in these systems, but definitely not as much as the Affinity laws would suggest. So I'm calling this myth, as it applies to most HVAC systems, busted.
Thanks, Lee. It's good to get that off your chest. Now, we've all likely heard the phrase, ride the fan curve. If a fan indeed follows a curve in this manner, what happens when we have a flat fan curve? Will a small change in pressure have a huge impact on airflow? Will a flat fan curve make it easier for a fan to stall or surge? Dustin?
To answer these questions, let's start with an example. A first impression of the highlighted region shown might be that a range of airflows are possible with a minimal change in static pressure. In this example, only 0.1 inches of water separate 8,000 CFM and 11,000 CFM. As the operating point nears the do not select region, one might also start worrying about stall or surge. This impression assumes the fan rides the curve and incorrectly assumes that the airflow is somehow dependent on the static pressure. As a result, an engineer may choose to select a fan not near but far to the right of peak pressure, an inefficient region to operate a fan. This is a classic know enough to be dangerous type of situation. A basic understanding of how a fan curve is developed can result in an incorrect interpretation of how a fan and a system interact. Fan performance testing is done at a given fan speed. For each test point, fan airflow is set by the test chamber exhaust. Accurate measurements of airflow, pressures, temperature, and so on are recorded, along with the power required at the fan shaft. These data points are then used to construct a fan curve and brake horsepower curve for a specific fan in a test chamber at one speed and at one air density. So when a constant speed fan is controlled by a simple discharge damper, the fan can indeed ride the fan curve, similar to how fan performance testing is accomplished. Even with a damper, however, small changes in pressure won't affect the airflow significantly. Let's investigate why that is. The first concept to understand is that the fan is dependent on the system. The system will determine where the fan operates on a fan curve. Therefore, regardless of what fan is selected, or how flat or how steep the fan curve may be, the system will determine a single point that the fan must operate at. What the fan does control, however, is if the intended design point can be met, and what fan parameters are needed to meet the system conditions. The y-axis, the dependent variable, represents pressure. It is dependent on the airflow represented by the x-axis, the independent variable. In other words, for a given airflow, the system will have a total resistance equal to the pressure, not the other way around. In the pump industry, it's often said that pumps make pressure and valves control flow. A similar concept applies to fans as well. The only time a fan will ride the fan curve is if the system changes, as is the case when a fan is being controlled by a simple discharge damper or when a filter gets changed or loaded. Let's revisit our example where we had identified two different systems. Let's suppose the system at design was expected to have an output of 3.25 total static pressure at 11,000 CFM. Instead, a field measurement has the fan operating on a different system with an output of 3.25 total static pressure at 8,000 CFM. To get the fan to operate at the design CFM of 11,000, the actual system must have a resistance higher than 6 inches for the design airflow of 11,000 CFM, a far cry from the 0.1 inches we were originally worried about. Again, the fan is dependent on the system, and the system determines where the fan operates on a fan curve. Now that we have that concern behind us, let's talk about what a flat or steep fan curve really means. Operation on a steep fan curve can minimize the effect of a misestimated system. In other words, a smaller decrease in flow will be realized if the system pressure is misestimated. Likewise, a smaller increase in speed and power will be required to get back to the desired airflow. In the steep fan curve shown, a 0.5 change in static pressure will result in a 6.3% loss in airflow. Let's now look at a flat fan curve. For the same 0.5 inch change in static pressure, the airflow changes by 6.7%, or double that of the steep fan curve. Fan types that normally have flat fan curves, forward curved for example, are the most forgiving when it comes to stall or surge conditions. However, a steeper fan curve, airfoil for example, can minimize the effect of a misestimated system. So is it true that small changes in pressure can have a huge impact on airflow? No, this myth has been busted. As we've seen, this myth comes from a misunderstanding of how to interpret a fan curve. The truth is that the fan is dependent on the system, and the system will determine where the fan operates on a fan curve. As we saw earlier, for a given airflow, the system will have a total resistance equal to the pressure, not the other way around.
Thanks, Dustin. So, Mick, I hear that for a chilled water system to be efficient, it needs to be variable primary flow. Do you have any thoughts on this?
Yep, I do. Bill Bonfleth and Eric Pyre at Penn State did research and found the savings noted on the slide. This is truly a value engineering proposition. The installed cost and operating costs are both lower. Now they compared variable primary flow systems with primary secondary systems. But there are times it might not make sense to design the system as variable primary flow. For example, if the chiller and air handler are in the same equipment room, there's very little pump energy to be saved. So variable flow may not be warranted at all. In such cases, you can still install a variable speed drive on the pump, but use that drive just to set design flow rate and open any balancing or triple duty valve. It's just increasing pressure drop and pump energy. Then instead of varying water flow rate, reset the chilled water temperature to control the coil leaving air temperature. This saves compressor energy. And one more option, if the system is going to be constant flow, expand the delta T so the system flow rate is even lower. This reduces pump power even more. So in applications where the pump power is low, this may be a better application. Next, if the minimum evaporator flow rate is very nearly the design flow rate, there isn't as much pump energy savings available because water often has to be bypassed to maintain that minimum flow rate. As examples, this can happen if the system was designed using the ASHRAE Green Guide direction of 16 to 18 degree delta Ts. Or now, with the publication of ASHRAE 90.1 2016, the requirement for at least a 15 degree chilled water delta T. And with chillers that have limited evaporator choices, such as screw and scroll chillers. In VPF systems, we really like to have the turn down ratio, that is the ratio of design to minimum flow, be greater than 2. For a single chiller, the turn down ratio should be above 1.3, or it's probably not a good VPF candidate. And with 2 chillers, we'd put that number at 1.5 or higher. First, because the flow can't decrease very far, pump energy savings are low. And second, the bypass valve has to open during chiller transitions. Operators may not understand this and attempt to manually control the plant. Manual operation and VPF did not play well together. If there are only 2 chillers in the plant, consider piping them in series. The upstream chiller operates more efficiently, which overcomes increases in pump energy. But what's really great is the flow rate transition is 0 when the second chiller is enabled. So system operation is simpler. Now, how about converting a plant from primary-secondary to VPF? If the entire chilled water plant is being gutted anyway, it's like a new plant. So designing it as a variable primary flow system allows you to realize the savings estimated by the Penn State study. Now, I've seen conversion to VPF make sense when more cooling capacity is needed. When the primary pumps are removed, a lot of space is freed up. At a university out east, an additional 1,000-ton chiller was installed where those primary pumps used to be. Now, in a landlocked chilled water plant, that saved a lot of capital cost. But if there is enough cooling capacity and planned piping changes are minimal, conversion to variable primary, variable secondary actually makes a lot of sense. The basic premise of variable primary, variable secondary is to match the primary flow and the secondary flow to save that pumping energy. So, to convert to VP/VS, first, add variable speed drives to the primary pumps. And while you're at it, open that balancing portion of the triple duty valve wide open. Use the pump VSD to balance the design flow rate. That sets the maximum pump speed. Now, you'll likely save energy just by doing those things. Next, if they aren't already there, install temperature sensors in the return line from the system and to the chiller. Control the primary pump variable speed drives so that the return temperature to the chillers is a little lower than from the system. This matches the primary and secondary flow, but ensures a little excess flow in the bypass line all the time. That means the system chilled water set point is always maintained. Finally, install flow sensing devices such as DP sensors at each chiller to ensure minimum flow rate. If the temperature control of the pump variable speed drive results in flow approaching the chiller's minimum, override that temperature signal with a flow signal to stay above the chiller's minimum flow rate. Finally, you may want to avoid VPF if the operator doesn't understand the plant and wants to manually control it. In general, again, manual control and VPF do not fit well together. Designing the system for constant chiller evaporator flow with chilled water reset or primary-secondary may keep you from getting callbacks to the job. So this myth is kind of busted. While variable primary flow makes sense in many chilled water plants, there are applications where other options are simpler and give good return on investment.
Thanks, Mick. Now, one of the most common problems encountered with equipment after installation is being short on airflow. The first inclination is to blame the fan. It's what's providing the air, after all. Now, Dustin, you're the fan expert here. How likely is it that the fan is causing the problem?
To properly answer these questions, let's start with a discussion on how a fan is tested. AMCA Standard 210 details how to test fans in the lab, how to rate fan performance, and how to construct fan curves from the test data. Many manufacturers use the test configuration shown here. It can produce highly accurate airflow measurements over a wide range of flows, as well as very accurate pressure and power measurements. Tests run using this setup usually provide the most accurate fan performance data available. Turbulence caused by airflow restriction at either the fan inlet or outlet, or non-uniform air distribution, can negatively impact the performance of a fan when it's installed in an air handling unit or connected to a duct system. This is commonly called system effect. System effect prevents the fan from operating as it did under laboratory rating conditions. System effects related to the fan inlet or outlet generally occur when the air is not allowed to establish a uniform velocity profile. The discharge off a house fan is a classic example. A house fan will develop a uniform velocity if connected to a duct that is sized the same as the fan discharge and is sufficiently long. If there's not enough space to fully develop, a system effect will be realized. Here's an often overlooked example of system effect: a free and abrupt discharge off a house fan embedded in a larger piece of equipment. That is, a situation where the fan is not the last section in the airstream, typical of units with blow-through components or return fans. A house fan is designed for and tested with a duct connection that's about the same size as the fan discharge. If the duct isn't present, the fan performance will deviate significantly from the AMCA 210 test. Any pressure measurement taken downstream of the fan won't include this effect. This loss can be significant, as high as 1 inch in some cases. As I mentioned, a system effect prevents the fan from operating as it did under laboratory rating conditions. But generating a new fan performance curve for every possible system effect would be too cumbersome and confusing. So for simplicity, AMCA has published system effect correction factors to help design engineers account for many of these effects before the fan is selected and installed. These correction factors are like effective pressure drops that are added to the estimated static pressure loss for the rest of the system when selecting a fan. So let's discuss some common system effects. If an open discharge, an elbow, a branch, turning vanes, or a damper is located too close to the fan outlet, this effect should be accounted for during fan selection. A good rule of thumb is to ensure these components are at least 3 fan diameters downstream. Likewise, if an elbow, turning vanes, air straightener, or other obstruction is located too close to the fan inlet, this system effect should also be accounted for. The effects of pre-swirling the air prior to entering the fan wheel or the use of an inlet plenum are other examples. Note that flex duct is particularly problematic. The flex duct should have about a ½ inch of give if depressed with a finger. Significant folding or excess length can detriment the performance of the fan. Manufacturers of air handling units or packaged rooftops typically account for many of these effects when they occur within a larger manufactured assembly. For example, in a draw-through air handling arrangement, the effects of the surrounding cabinet are typically included when determining and cataloging fan in-unit performance. The bigger challenge for a design engineer is the effect of unit inlet and discharge duct connections or any components that are added in the field. We've seen how a fan is tested and how to account for deviations from those tests. Let's move on to investigate some of the more common problems. Considering all the variables involved with duct design and installation, it's not unreasonable to expect an actual system to have a higher pressure loss than expected. Difficult installation conditions, unexpected duct system resistance, and hidden system effects are all common problems encountered. It's hard to predict from a drawing how a duct system will actually work after it's installed, but duct sizing programs can do this pretty well. If you rely on rules of thumb to estimate system total static pressure, you may find it necessary to increase the motor horsepower after the fan is installed. And architects always seem to want small equipment rooms. Tight spaces lead to less than ideal duct connections at the air handler. The resulting system effect must be accounted for during design or dealt with after installation. And speaking of installation, don't forget to visit the construction site and monitor duct installation practices. Even innocent modifications can unexpectedly change system resistance, result in a system effect, or both. Leaks are another common problem, primarily in the unit connections or in the duct systems, but potentially at the fan bulkhead wall as well. The next one could be easy. Simply review the sticker on the fan to ensure the fan is spinning in the correct direction. If no sticker is present, or if there's a suspicion it was placed incorrectly, it's not hard to determine the proper rotation of a fan. Most fan types are intended to operate in a specific direction. use the following guidelines to determine proper rotation. If the fan in question is forward curved, the fan should cup the air as shown. If the fan is backward tended, as is the case with backward inclined, backward curved, or airflow fan types, the fan should slap the air as shown. Another cause of low airflow is the result of an electrical system that has been maxed out. If the system seems to be operating as expected, but the current is higher than expected, there are a few problems to consider. It is possible that there's a bad component. A bad bearing or a bad motor could cause higher than expected power draws. Installation issues like wheel cone overlap and an over-tightened belt can also cause additional power losses. Now the less common problems. It is possible that the wrong fan could be installed. This can generally be verified by reviewing the fan's nameplate and/or making some measurements. In the case of a house fan, there could be a problem with the fan cutoff. Note that fan cutoffs, a critical component for the efficient operation of a house fan, come in different shapes and sizes. A 3-piece cutoff with the top 2 pieces split is shown here. Although unlikely, another possibility is a software or catalog error. The nice thing about fans is that they are very predictable and follow the fan affinity laws. Although it's theoretically possible that there's some underlying physics that could be the culprit for a low airflow problem, it's highly unlikely. Any investigation should start with measurement of the 4 basic fan parameters: airflow, pressure, speed, and power, the latter indirectly by measuring volts and amps. If measuring motor power parameters between a VFD and a motor, be sure to use a true RMS meter to account for the modulated waveform. VFD settings in general can be tricky. Energy optimization and variable torque versus constant torque are 2 common settings that can trip up a power measurement. It's best to run the VFD in bypass mode or at line hertz whenever possible to minimize the variables. If the unit being evaluated includes a return or exhaust fan in addition to a supply fan, be sure to safely isolate each fan by shutting the return air damper completely to ensure the other fan isn't affecting the fan in question. Finally, be sure to understand parameter measurement error. Measurements of airflow and pressure are tricky. For airflow, a traverse of the coil or a traverse of a duct with a fully developed flow close to the fan or unit is ideal. A sum of VAV box airflows is not a measurement that can be used to verify fan airflow. Too many variables, including duct leakage, can influence this measurement. Speed, and in many cases power, are much easier to get right. If all 4 parameters don't align on the fan curve, the speed and power information should thus be trusted more and reasonable ranges applied to the other parameter measurements. Some designers want to verify fan performance in the field to make sure the fan works as predicted by the manufacturer's fan curve. I always want to ask, does your duct system really look like this test chamber? Because if it doesn't, the as-installed fan curves won't be the same as the catalog fan curves. It's simply not easy to duplicate published fan curves in the field. AMCA 203, a publication included in the AMCA Fan Application Manual, includes detailed guidance for designing and performing field tests. As we discussed, taking measurements in the field can be difficult, and you don't always have access to the right measurement location. So it's key to understand how to make the necessary corrections. But rest assured, field performance tests are never easy and not nearly as accurate as lab tests. So although verifying fan performance in the field is not impossible, it's probably not your first course of action for correcting airflow problems. For more help solving airflow shortfalls, you should turn to the AMCA publications, especially the 4 included in the AMCA Fan Application Manual. They can help you discover problems and devise solutions. We've mentioned AMCA Publication 201, Fans and Systems, already. This publication lists several possible causes for insufficient airflow, all of which seem to relate to either duct design, system installation, field measurement problems, or system effect. As we've discussed, it also includes extensive guidance for proper system effect accounting. AMCA Publication 202, Troubleshooting, includes checklists and recommendations to help you troubleshoot and correct problems found in fan installations. It adds to the list of possible causes we've been discussing. For instance, the fan may have been damaged prior to installation, or it may not be properly wired or controlled. For more information on system effect and fan operation in general, see the Fans and Air Handling Systems Engineers Newsletter Live materials. So is it true that the fan's almost always at fault when it cannot deliver the airflow it's supposed to? The answer is, it depends. As we've seen, it's much more likely that the system pressure has been misestimated or hidden pressure losses like system effect are being unaccounted for. However, there are still many situations where the fan can be at fault.
Thanks, Dustin. The last myth we'll cover today has to do with energy saving claims. Mick, what's the reality?
A lot of people claim you can save, you fill in the blank, some percent of energy just by doing whatever is being sold or touted. There's a saying that 40 is the new 30, and we're finding it to be very true. Heck, Lee and I hope that 60 is the new 40. But today it seems to get someone's attention that technology can't save 10 or 15 or even 30% of energy use. It needs to save a lot more. Let's look at some examples, mostly from recent ASHRAE journal advertisements, but I'll throw in one I found online. So let's start with the low numbers with respect to savings claims. Do I have 30%? Piece of cake. How about 35? But we're just starting. 40% savings is becoming much more commonplace, and well, we can go beyond 40% too. How about 47% or even 54%? Who wouldn't want to reduce their energy consumption by more than half? And now my personal favorite, savings of 78.5%. And to think that on the 90.1 2010 committee, we found 30% a challenge. So sign me up at 78.5%. Now, I'm not saying any of these ads are wrong or incorrect, because someone, somewhere, had to do a calculation and hopefully get it by their legal counsel to publish. But as engineers, we need to make sure that when claims are made, we engage the analytical side of our brains so the clients actually get what they're being promised or sold. So in examining such savings claims, the first question we should ask is, compared to what? If we take a system designed to today's energy efficiency requirements, using today's controls, and perhaps even with lower capacity because buildings are more efficient, but we make our baseline an unoptimized system from the 1980s, well, if we can't get to 30%, we aren't even trying. So make sure that comparable and current systems and technologies are used in both the base and comparison system. Sometimes we'll read about huge savings due to retrofitting with some gadget or widget, and those savings may be valid. But a question to ask is, what else got done? Was the cottonwood cleaned off the condenser coils, unclogging them for the first time in 5 years? Was a refrigerant charge corrected? Were clean filters finally installed, allowing air to actually blow across the evaporator after years of deferred, or was that ignored maintenance? And finally, is the comparison valid for your specific project in your location? As we covered in the ENL last year, using something like IPLV for chiller comparison is too simple, since it's the same in every climate and building, and not even close to accurate. So use the right tool for the job. Let's take that 78.5% claim. Now we compared indirect evaporative cooling with compressor cooling. If a project is in a dry location, water is available, and the right conditions are encountered, those savings are available. With that said, a project in the United States and east of the Rockies, or in the Caribbean, or somewhere like Malaysia, well, this technology probably isn't a good fit, and the stated savings won't be realized. The bottom line questions are, does the solution meet my customer's needs? If required, is a long-term commitment acceptable for your client? Will they be able to realize and keep realizing the savings? So this myth may not be busted, but we need to perform our due diligence. As we do with any other solution we bring to our customers, Let's make sure the baseline is valid and the comparison is realistic. Analysis is often needed, yet you don't get paid enough to spend weeks on that. Check out last year's E&L for solutions that can help you help your customers in a short period of time, using analysis tools that are appropriate for the applications. And most importantly, understand your client's needs, abilities, and business, and give them the information they need to determine if the solution helps them, both now and in the future.
Thanks, Mick. As always, we have a number of resources available that provide more information on all of the topics covered today. The bibliography included in your handout provides more information on where to find all of these resources, including past E&Ls, many of which are available as continuing education credit programs on demand and free of charge. Visit trane.com/continuingeducation for a complete list to satisfy credentialing requirements. And don't forget to fill out a survey and let us know how we did today. Finally, ask your local host about details for the remaining Engineers Newsletter Live programs this year. In fall, we'll be discussing high-performance airside systems and demand response in commercial buildings. So please plan to join us. Thanks for your time today. We look forward to seeing you next time.